These are notes for Malham's Math 60 for Tuesday, April the 7th, section 7.5, page 637. We are solving radical equations. That means there are square roots or perhaps cube roots and an equal sign, so we're solving for the variable. It turns out for all of these problems, once you get a proposed solution, you need to check this solution, whether the direction says so or not, because sometimes the proposed solution works and sometimes it doesn't. The only way you can tell for sure is to substitute back in your proposed solution into the original. And I'll give you some examples where the proposed solution works and where sometimes it doesn't work, which means it's critical every time that you get a proposed solution to check your proposed solution to see if it works. Problem 15, the square root of a minus 3 equals 1. To get rid of the square root symbol, we square both sides, because if you have a square root squared, you basically just take off the square root and you end up with a minus 3. So squaring both sides, the left-hand side becomes just a minus 3. The right side, 1 squared is equal to 1. Now we have a very easy equation. Add 3 to both sides, a is equal to 4. So my proposed solution is 4, but you better check to see if it works. Sometimes it works, sometimes it doesn't. So how can you tell? We just substitute in. So put 4 back into the original equation. Is the square root of 4 minus 3 equal to 1? And I usually put a question mark here when I'm doing a check. We're not claiming that they're equal. The question mark means we're checking, is it equal or is it not equal? The square root of 4 minus 3 is the square root of 1. The square root of 1 is equal to 1. So in this case, the proposed solution checks. So a equals 4 is indeed the solution. Let's try problem 23. The square root of 2x plus 1 plus 2 equals x. Now before I square both sides, I don't want that 2 there, so I'm going to subtract 2 to both sides, because when I square both sides, I would rather just have a regular square root, not square root plus something or minus something. So square root of 2x plus 11 equals x minus 2. Now I'll square both sides. So I square here and I square here. Again, the square root of a square just gives me 2x plus 11. This side, x minus 2 squared, is x squared minus 4x plus 4. Again, you can either multiply x minus 2, or use the shortcut formula. I'll let you do either way that you wish. And now I have an equation that doesn't have any square roots in it. It's a quadratic equation. That means there's a square there. So I want to put everything on one side and 0 on the other. So I'll put a 0 on the left side, subtract 2x, and also subtract 11 on both sides, giving me 0 equals x squared minus 6x minus 7. This factors into x minus 7, x plus 1 equals 0. Then by the 0 factor property, that means either this expression is 0 or this expression is 0. And the number that makes this expression 0 is 7. And the number which makes this expression 0 is negative 1. So my proposed solutions are 7 and negative 1, but again, let's check. So I try 7 back in the original equation, back here and here. So put a 7 here and a 7 here. Gives me square root of 2 times 7 plus 11, plus 2 is equal to 7. 2 times 7 is 14, plus 11 is 25, so I'm taking the square root of 25, plus 2 equals 7. That does work, and these are question marks saying is it or is it not equal. And 5 plus 2 equals 7, that's a true statement. So x equals 7 is a solution, but let's try negative 1. So I plug in negative 1 here and here. 2 times negative 1 plus 11 plus 2, is that equal to negative 1? That gives me negative 2 plus 11 plus 2, is that equal to negative 1? Square root of 9 plus 2, that's certainly not equal to negative 1. Square root of 9 is 3. 3 plus 2 is not negative 1. So I reject negative 1 as a solution. It's not a real solution after all. So the only real solution is x equals 7, because negative 1 does not check. So you can see we have to check our answers as we go along. Back up here, square root of 5x plus 10 equals 8. Again, before I square both sides, I want to get rid of that 10, so I subtract 10 on both sides. 8 minus 10 is negative 2. So square root of 5x equals negative 2. Now I square both sides. The square root of 5x squared is just 5x. Negative 2 times negative 2 is a positive 4. For emphasis, I put a positive 4 there. Divide both sides by 5. X equals 4/5. But upon further examination, if I double check and plug in 4/5 right there, I get square root of 5 times 4/5 plus 10 equals 8. 5's cancel. I have the square root of 4 plus 10 equals 8. Square root of 4 is 2. 2 plus 10 is certainly not equal to 8. So that's not a solution. So there is no solution. So we say no solution, or you can put the 0 with a slash, meaning empty set. It's probably a little bit easier to write that. It's less writing. But in this particular instance, we have no solution. 35 is our first instance where you don't have a square root, you have a cube root. Cube root of 7 minus n equals 3. So over here, to get rid of a square root, you square both sides. So likewise, to get rid of a cube root, you cube both sides. So when I have a cube root cubed, that cancels out the cube and the cube root. So I cube both sides. So I just have 7n minus 1. And then on this side, 3 cubed is equal to 27. Now I have a fairly easy equation. Add 1 to both sides, 7n equals 28. Divide both sides by 7, n is equal to 4. Again, check your proposed solution. Plug in 4 right here. Square root of, cube root of 7 times 4 minus 1, is that equal to 3? 7 times 4 is 28, minus 1 is 27. The cube root of 27 is indeed 3, so this checks. So our proposed solution, n equals 4, is good. Coming up here to question 41, they give the question in sort of a roundabout way. They give you a function, f of x is equal to 4th root of 3x plus 1, and they ask for what x value will f of x equal to 4. So I basically just plug in 4 right here. So my equation becomes 4 equals the 4th root of 3x plus 1. Well, to get rid of a square root, we square both sides. To get rid of a cube root, we cube both sides. So how do you get rid of a 4th root? You raise both sides to the 4th power. 4th power here, 4th power here. And in case you're wondering, there's no fancy word for raising to the 4th power. To raise something to the 2nd power, we say square. To raise something to the 3rd power, we say cube, but there's no special term for 4th power, 5th power, 6th powers. We just say raise to the 4th power. So the 4th root of 3x plus 1 to the 4th power just cancels that symbol out, and I just have 3x plus 1. 4 to the 4th, you can punch it in your calculator. 4 times 4 times 4 times 4 is 256, and now I have a fairly easy equation. Subtract 1 on both sides, 255 equals 3x. Divide both sides by 3, x is equal to 85. And notice the convention, I'm writing the variable that you're solving for on the left side. Again, check your answer, plug in 85 to the original to see if it works. So is 4 equal to, that's a question mark, the 4th root of 3 times 85 plus 1. Punch it in your calculator, 3 times 85 is 255. Add 1, you get 256. The 4th root of 256 is indeed 4, because you're asking for the 4th root of 256, what number raised to the 4th power gives me 256? The answer is 4. So x equals 85 is a good solution. 53, they write the original problem as a fractional exponent, but you might recall if you raise something to the 1/3 power, it means the same thing as cube root. This is the power, 1 is the power, 3 is the root. So raising something to the 1 means don't do anything, and then I take the cube root. So it's the same as saying cube root of 34x plus 26 equals 4 times the cube root of x minus 1. And once again, to get rid of a cube root, I cube both sides. So raise all of this to the 3rd power, raise all of this to the 3rd power, the cube. This side just simply becomes 34x plus 26. The cube root and the cube cancel out. Here, the cube root of x minus 1 cubed is x minus 1, but I do have to figure out 4 cubed. 4 cubed, 4 times 4 times 4 is 64. So I have this equation now, but at least there's no more radicals in there. Distribute over here, 34x plus 26 equals 64x minus 64. And I want to get the x's on the right side, and that means the numbers on the left side. So I subtracted 34x on both sides. That leaves me with a 30x here, and I'll add 64 to both sides. 90 equals 30x. Divide both sides by 3. X is equal to 3. Check against the original, so I'll plug in 3 right here, plug in 3 right here. 34 times 3 plus 26 raised to the 1/3 equals, question mark, 4 times 3 minus 1 to the 1/3. 34 times 3 plus 26 comes out to be 128. 3 minus 1 is, of course, 2. This means cube root. So cube root of 128, I can write it as the cube root of 64 times 2. And the cube root of 64 is 4. So I'm left with 4 times the cube root of 2, which is exactly what we have over here. 4 times 2 to the 1/3 means 4 times the cube root of 2. So it does check. So x equals 3 is a good solution. And finally, for 55, it's a little bit harder. Here's an instance where you actually have to square both sides twice to get rid of both radicals. Radical x minus 5 plus radical x equals 5. Now, normally you wouldn't want to square an equation like this because you've got a radical here and a radical here. That's too much on one side. So I start by subtracting radical x on both sides. So when I square both sides, at least this one comes out nice. This one would still not be nice, but at least it's a little bit better than what I would have had if I square it from here. So now I square both sides over here, and the square root of x minus 5 squared is just x minus 5. This one's harder. If I square this, I have to use the shortcut formula. It's parentheses a minus b squared. The root for that was a squared minus 2ab plus b squared, you might recall. Or you can just FOIL out 5 minus root x times another 5 minus root x. It gives me 25 minus 10 radical x. This is the 2ab term, minus 10 radical x, plus b squared, radical x squared, is just x. Subtract x from both sides, so these are gone. Subtract 25 from both sides, so the right-hand side just has negative 10 radical x. The left side is negative 5 minus 25, which is negative 30. Divide both sides by negative 10. 3 equals radical x. Square both sides again, so we have to square twice. And now we have 9 equals x, or x equals 9. And now we check again. So remember, all of these have to be checked. So we'll plug in 9 back here and here. Square root of 9 minus 5 plus the square root of 9 equals question mark 5. 9 minus 5 is 4. Square root of 4 plus square root of 9 is equal to 5. Square root of 4 is 2. Square root of 9 is 3. 2 plus 3 is indeed 5. So our proposed solution does work. So this is Malham's Math 60, Tuesday, April the 7th, section 7.5, page 637. Again, I'm going fast to make the video shorter. You can always fast forward or rewind as much as possible. Again, if this is too small for you or you can't see it easily, remember it's easier to look in front of you, the full-size version. I always give you this attachment, so ideally if you could say print it out and you can look at this and just listen to the audio as I point certain things out as we go through the notes.